Shot is a collective term for small balls or pellets, often made of lead. These were the original projectiles for shotguns and are still fired primarily from shotguns and less commonly from riot guns and grenade launchers, although shot shells are available in many pistol calibers in a configuration called bird shot, rat shot, or snake shot. Lead shot is also used for a variety of other purposes such as filling cavities with dense material for weight/balance. Some versions may be plated with other metals. Lead shot was originally made by pouring molten lead through screens into water, forming what was known as swan shot, and, later, more economically mass-produced at higher quality using a shot tower. The Bleemeister method has supplanted the shot tower method since the early 1960s. Manufacture. Producing lead shot from a shot tower was pioneered by William Watts of Bristol, who adapted his house on Redcliffe Way by adding a 3-story tower and digging a shaft under the house through the caves underneath to achieve the required drop. The process was patented in 1782. The process was later brought above ground through the building of shot towers. Molten lead would be dropped from the top of the tower. Like most liquids, surface tension makes drops of molten lead become near spherical as they fall. When the tower is high enough, the lead droplets will solidify while still dropping and thus will retain their spherical form. Water is usually placed at the bottom of the tower, causing the lead to be cooled immediately after dropping. Roundness of manufactured shot produced from the shot tower process is graded by forcing the newly produced shot to roll accurately down inclined planes. Unround shot will naturally roll to the side, for collection. The unround shot was either reprocessed in another attempt to make round shot using the shot tower again, or used for applications which did not require round shot, e.g., split shot. The hardness of lead shot is controlled through adding variable amounts of tin, antimony, and arsenic, forming alloys. This also affects its melting point. Hardness is also controlled by the rate of cooling that is used in manufacturing lead shot. The Bleemeister method, named for inventor Louis W. Bleemeister of Los Angeles, CA, U.S. Patent 2,978,742, dated April 11, 1961, is a process for making lead shot in small sizes from about number 7 through about number 9. In this process, molten lead is dripped from small orifices and dropped approximately 1 inch, 2.5 centimeters, into a hot liquid, where it is then rolled along an incline and then dropped another 3 feet, 91 centimeters. The temperature of the liquid controls the cooling rate of the lead, while the surface tension of the liquid and the inclined surface, S, work together to bring the small droplets of lead into highly regular balls of lead in spherical form. The size of the lead shot that is produced is determined by the diameter of the orifice used to drip the lead, ranging from approximately 0.018 inches for number 9 lead shot to about 0.025 inches for number 6 or number 7.0 shot, while also depending on the specific lead alloy that is used. The roundness of the lead shot depends on the angle of the inclined surfaces as well as the temperature of the liquid coolant. Various coolants have successfully been used, ranging from diesel fuel to antifreeze and water-soluble oil. After the lead shot cools, it is washed, then dried, and small amounts of graphite are finally added to prevent clumping of the lead shot. Lead shot larger than about number 5 tends to clump badly when fed through tubes, even when graphite is used, whereas lead shot smaller than about number 6 tends not to clump when fed through tubes when graphite is used. Lead shot dropped quickly into liquid cooling baths when being produced from molten lead is known as chilled lead shot, in contrast to soft lead shot which is produced by molten lead not being dropped as quickly into a liquid cooling bath. The process of rapidly chilling lead shot during its manufacturing process causes the shot to become harder than it would otherwise be if allowed to cool more slowly. Hence, chilled lead shot, being harder and less likely to deform during firing, is preferred by shotgunners for improving shot pattern densities at longer, 30-yard, ranges, whereas soft lead shot, being softer and more likely to deform during firing, is preferred for improving shot pattern densities at very close, 20-yard, ranges as the softer and now deformed shot scatters more quickly when fired. Soft lead shot is also more readily deformed during the firing process by the effects of chokes. The manufacture of non-lead shot differs from that of lead, with compression molding used to create some alloys. Sizes. Shot is available in many sizes for different applications. The size of numbered shot decreases as the number increases. In hunting, some sizes are traditionally used for certain game, or certain shooting situations, although there is overlap and subjective preference. The range at which game is typically encountered and the penetration needed to assure a clean kill must both be considered. Local hunting regulations may also specify a size range for certain game. Shot loses its velocity very quickly due to its low sectional density and ballistic coefficient, see external ballistics. Generally, larger shot carries farther, and does not spread out as much as smaller shot. Buckshot. Buckshot is simply shot formed to larger diameters so that it can be used against bigger game such as deer. Sizes range in ascending order from size number B to tri-ball. It is usually referred by the size, followed by buck, e.g. number 000 is referred to as triple-aught buck in America or triple-O buck in other English-speaking countries. Buckshot is traditionally swaged, in high-volume production, or cast, in small-volume production. The Bleemeister method does not work for shot larger than number 5, and works progressively poorly for shot sizes larger than about number 6. Applications outside firearms. Lead shot is also often used as ballast in various situations, especially where a dense, pourable weight is required. Generally, small shot is best for these applications, as it can be poured more like a liquid. Completely round shot is not required. When used as a pourable/moldable weight, the shot may be left loose, or mixed with a bonding agent such as epoxy to contain and stabilize the pellets after they are poured. Some applications are stress testing, providing variable weights and strength of materials stress testing systems. Shot pours from a hopper into a basket, which is connected to the test item. When the test item fractures, the chute closes and the mass of the lead shot in the basket is used to calculate the fracture stress of the item. Hydrometers use a weight made of shot, since the weight has to be poured into a narrow glass vessel. Split shot, a larger type of lead shot where each pellet is cut partway through the diameter. These type of shot were formerly commonly used as a line weight in angling. They are no longer solely manufactured from lead but instead are often made from softer materials that can be easily pressed onto the fishing line instead of being closed in a crimp using pliers as was once common. The heads of some dead blow hammers are filled with shot to minimize rebound off the struck surface. Shot belt. Some scuba diving weight belts contain pouches filled with lead shot. Speaker stands can be filled with lead shot for additional acoustic decoupling, as well as stability. Model rocketry, to add weight to the nose of the rocket, increasing the stability factor. Due to its relatively high heat capacity and low thermal conductivity at low temperatures, lead shot has been used as a suitable material for a regenerator in Stirling engines and thermoacoustic cryocoolers. Due to lead's high density, it is used to attenuate radiation, especially X-rays and gamma rays. Lead shot may be enclosed in a bag and then be placed around a point source for radiation protection or for radiation shielding. Bird lead poisoning. Lead shot-related waterfowl poisonings were first documented in the U.S. in the 1880s. By 1919, the spent lead pellets from waterfowl hunting was positively identified as a major source of deaths of bottom-feeding waterfowl. Once ingested, stomach acids and mechanical action cause the lead to break down and be absorbed into the body and bloodstream, resulting in death. If a bird swallows only one pellet, it usually survives, although its immune system and fertility are likely to be affected. Even low concentrations of lead have a negative impact on energy storage, which affects the ability to prepare for migration. Upland game birds such as mourning doves, ring-necked pheasants, wild turkey, northern bobwhite quail and chicars can also ingest lead and thus be poisoned when they feed on seeds. As scavengers, Californian condors eat carcasses of game that have been shot, but not retrieved, and with them any fragments of lead. This in turn increases the lead levels in their bodies, leading to secondary lead poisoning. Among condors around the Grand Canyon, lead poisoning because of eating lead shot is the most frequently diagnosed cause of death. Restrictions on the use of lead. Depending on hunting laws, alternatives to lead shot are mandated for use by hunters in certain locations or when hunting migratory waterfowl and migratory birds or when hunting within U.S. federal waterfowl production areas, U.S. national wildlife refuges, or some state wildlife management areas. Lead shot is also banned within an 8-county area in California designated as the Condor's Range. As of 2011, 35 states prohibited lead shot use in such specially specified areas when hunting. While hunting non-migratory or upland birds, as well as animals, in the United States, lead shot is generally approved, except within the specially designated non-toxic shot pellet zones. In an effort to protect the condor, the use of projectiles containing lead has been banned for hunting deer, wild pig, elk, pronghorn antelope, coyotes, ground squirrels, and other non-game wildlife in areas of California designated as its range. The bald eagle has similarly been shown to be affected by lead originating from dead or wounded waterfowl. The requirement to protect this species was one of the biggest factors behind laws being introduced in 1991 by the United States Fish and Wildlife Service to ban lead shot in migratory waterfowl hunting. Hunting restrictions have also banned the use of lead shot while hunting migratory waterfowl in at least 29 countries across by international agreement. For example, the Agreement on the Conservation of African Eurasian Migratory Waterbirds. Depending on hunting laws, alternatives to lead shot are mandated for use by hunters in some locations when hunting migratory birds, notably waterfowl. In the U.S., the restrictions are limited to migratory waterfowl, while Canadian restrictions are wider and apply, with some exceptions, to all migratory birds. The hunting of upland migratory birds such as mourning doves was specifically excluded from the 1991 U.S. restrictions as scientific evidence did not support their contribution to the poisoning of bald eagles. In 1985, Denmark banned the use of lead in wetlands covered by the Ramsar Convention, later expanding this restriction to the whole country. The use of lead has been banned for all hunting activities in the Netherlands as of 1992. The Missouri Department of Conservation introduced regulations in 2007 in some hunting areas requiring the use of non-toxic shot to protect upland birds. Some clay pigeon ranges in the U.S. have banned the use of lead after elevated levels of lead were found in waterfowl, small birds, mammals, and frogs in their vicinity. Non-toxic alternatives to lead shot. Approved alternatives while hunting migratory waterfowl include pellets manufactured from steel, tungsten iron, tungsten polymer, tungsten nickel iron, and bismuth tin in place of lead shot. In the United States, UK, Canada, and many Western European countries, France as of 2006, all shot used for hunting migratory waterfowl must now be non-toxic, and therefore may not contain any lead. Steel was one of the first widely used lead alternatives that the ammunition industry turned to. But steel is 100 times harder than lead, with only 2/3 its density, resulting in undesirable ballistic properties compared to lead. Steel shot can be as hard as some barrels, and may therefore damage chokes on older firearms that were designed only for use with softer lead shot. The higher pressures required to compensate for the lower density of steel may exceed the design limits of a barrel. Within recent years, several companies have created non-toxic shot out of bismuth, tungsten, or other elements or alloys with a density similar to or greater than lead, and with a shot softness that results in ballistic properties that are comparable to lead. These shells provide more consistent patterns than steel shot and provide greater range than steel shot. They are also generally safe to use in older shotguns with barrels and chokes not rated for use with steel shot, such as for bismuth and tungsten polymer, although not tungsten iron shot. Unfortunately, all non-lead shot other than steel is far more expensive than lead, which has reduced its acceptance by hunters. Non-toxic shot types approved by the U.S. Fish and Wildlife Service. Approved shot type % composition by weight. Bismuth tin 97% bismuth, and 3% tin. Iron, steel, iron and carbon. Iron tungsten any proportion of tungsten, and 1% iron. Iron tungsten nickel 1% iron, any proportion of tungsten, and up to 40% nickel. Tungsten bronze 51.1% tungsten, 44.4% copper, 3.9% tin, and 0.6% iron, or 60% tungsten, 35.1% copper, 3.9% tin, and 1% iron. Tungsten iron copper nickel 40 to 76% tungsten, 10 to 37% iron, 9 to 16% copper, and 5 to 7% nickel. Tungsten matrix 95.9% tungsten, 4.1% polymer. Tungsten polymer 95.5% tungsten, 4.5% nylon 6 or nylon 11. Tungsten tin iron any proportions of tungsten and tin, and 1% iron. Tungsten tin bismuth any proportions of tungsten, tin, and bismuth. Tungsten tin iron nickel 65% tungsten, 21.8% tin, 10.4% iron, and 2.8% nickel. Tungsten iron polymer 41.5 to 95.2% tungsten, 1.5 to 52.0% iron, and 3.5 to 8.0% fluoropolymer.
Please subscribe and thanks for watching.